All right, phase changes. So we talked about solid, liquid, gas. Going from left to right, you can see the ice cubes, the liquid gas, and then there should be water vapor on the right. So what you're going to do is you're going to write solid with an arrow, liquid with an arrow, and gas. Now we're going to talk about the phase changes. Those are states of matters. Solid, liquid, and gas are phase states. Phase changes are how we get between solid, liquid, and gas. So you're going to draw arrows pointing towards S, L, and G, and then you're going to write reverse arrows pointing the opposite way. And then you also need to make an arrow between solid and gas and solid. And then over the arrows, we're going to write the phase changes. So when you go from a solid to a liquid, on the bottom left, you can see melting, right? So we know that ice cubes melt. Now, when you go from liquid to gas, it's going to be evaporation or vaporization. Some people call it boiling, which is not quite correct, but it's okay. It's close enough because you have melting point and boiling point, so it makes sense. I understand where that comes from. But evaporation or vaporization. Now, working back the opposite way, when we have gas going to liquid, this is condensation. So you take your cool glass of iced tea and you go outside and water condenses on the outside of your glass. So that's water vapor condensing down to liquid. When you take liquid and put it in an ice tray and put it in the freezer, you make ice cubes. So we call that freezing. So those four are probably familiar to you. The two that are probably not are the ones that go from solid to gas and gas to solid. So when those two changes occur, so remember to make a big arrow, go over from solid to gas like a big rainbow, and then go from gas to solid like a smiley face, we are skipping the liquid state. So sometimes solids don't go into liquids and then become gases. They go directly from solid to gas. And when we have something that goes from solid to gas, we call that sublimation. S-U-B-L-I-M-A-T-I-O-N. Sublimation. Two great examples are your favorite mothballs. You throw some mothballs out somewhere, you can smell them. They don't melt and then become a gas. They go straight from solid to gas. The second example is dry ice. This is carbon dioxide in a block ice form, and it makes really cool like clouds and vapor, but it never melts. It goes directly from solid to gas. Now, going from gas to solid is a little bit more hard to come up with an example. There's not one in your everyday life that I have. It's used a lot in technology, electronics, and things like that. But that phase change is called deposition. D-E-P-O-S-I-T-I-O-N, like you're depositing something. You deposit money at a bank, it's deposition, or like a law deposition. And so very few examples in your everyday life that I know of. A lot of it's just electronics and creation of like semiconductor chips and things like that. So you need to know the 6 phase changes, and you need to know the relationship between solid, liquid, and gas. And you should draw this out on your notes, and then I will post what I used to remember these things when I was in your position of learning kind of Gen Chem material, and that way you'll have them. So we just talked about solid, liquid, and gas and the phase changes in between. So, and we've talked about heat, and we know that heat either has to be transferred, but there's 2 things that could happen when we add heat into a system, and this image illustrates it as well as the words on the left. So if we're starting off with water, so that's what this picture is on the right, and it's less than 0. If it's less than 0, we know that water freezes at 0, so anything in this first column is going to be ice. This is in your freezer, which is less than 0. Should be, to keep your food from spoiling. So we know that it's going to be an ice. Now, if I start heating up ice and I'm adding heat into the system, that's the entire x-axis is adding heat, the ice is going to start heating up. And that's going to be shown in a positive slope, so an increasing line with the word warming over it. Now at 0 degrees Celsius, something new is going to happen. The heat going into the system is not heating up the system, it's causing a phase change. So that's represented by the flat line, the flat blue line that says melting. And above that, you have phase change. So the two things that occur in the phase change are liquid water and solid ice. So both of them are found at the same time. And we know that. You take an ice cube out, you put it on the counter. For a while, it's going to be both ice and liquid until eventually it's all liquid. So after all of the ice has melted and become liquid, if we're still putting heat into the system, now the blue line is going to go back up, right? You can see the blue line is rising. And that's the temperature of the system is going to rise until it gets to the next important number, which is 100 degrees Celsius. Because at 100 degrees Celsius, we know that water will boil. Now, when you boil water on the stove, it doesn't get hotter than 100 degrees Celsius. It is going to stay at 100 degrees Celsius until, if you forget about the pot of water, all the water evaporates and then you're just left with the pot. So you can see here that once all of the water goes from liquid to gas, we have 100% water vapor. Okay? And then any heat that's going into the system, it's not going to cause a phase change. It's only going to heat up the system. So the two responses for adding heat into a system are either increasing the temperature, which we measure with a thermometer, or going into a phase change. During the phase changes, there's no perceived change of temperature. So if I had a thermometer and a beaker of water with ice, it's going to continue to rise, but only when the ice is not melting and the liquid's not boiling. You need to know how to label a diagram like that on the right and explain to me how the matter is responding to the heat going into the system. Okay? It's illustrated on the graph because you can see on the y-axis how the temperature increases as the heat increases. Interpreting information from graphs is a really important skill. It's a very important skill for elementary kids. They learn how to graph things, and then they learn how to interpret graphs. And they do that at a very young age. And so we need to be comfortable reading graphs as well. So you need to spend some time feeling comfortable reading this graph, knowing what the x and the y-axes mean. We've talked a lot about heat. We've talked a lot about temperature and phase changes, and this graph brings it all together. So last two topics are thermodynamics. So thermodynamics is the study of heat and its relationship to mechanical and other forms of energy. So when we study thermodynamics, we have two parts: the system, which is the beaker, and the surroundings, which is everything around the beaker. When we take the system and the surroundings and bring them together, we're going to call that the universe. So easy peasy. That's everything in our world. So it's like a formula. System plus surroundings equals the universe. Now for us, it's much easier to study our system. And if we know that all these conservation laws apply, whatever we measure about our system must also be true about our surroundings. So what's the first law of thermodynamics? The first law of thermodynamics states that it requires the energy be transferred between the system and the surroundings, and it must be conserved. It's a conservation of energy law that we just got done talking about. So for example, if you have a heater in a utility room heating up your living room, the energy is theoretically conserved. Now, there are some interesting other relationships where not all of if you think about the fuel efficiency of your car, why is it not 100% fuel efficient? Well, that's because some heat is lost in other ways. Like the engine will heat up, and that's consuming some of the energy that would then theoretically be used to power your vehicle. But we know that it's conserved in some way, even if it doesn't look in the same manner. So when we talked about wind energy, solar energy, it can transfer electrical energy. They can transfer from one kind of energy state to another, but we assume that everything is conserved. Now, the second law of thermodynamics is going to be familiar to us. It's the natural flow of energy, which is that heat flows from something with a higher temperature to objects with a cooler temperature. And in order for the heat to flow the opposite direction, it requires energy. So the best way to think about this is thinking about what happens to water. Water flows downhill from a higher to a lower point. It does not flow uphill. In order to get water uphill, you have to have a tractor, a pump, diesel, a person carrying buckets of water. Water flows downhill. It does not flow uphill. And the same thing with energy. Heat energy is going to flow from higher to lower. And that's the second law of thermodynamics, which we've talked about already. We just didn't necessarily call it a law at the time. The last term is entropy. Now, entropy is a measure of disorder of the universe, so how disordered it is. Now, we do know that the total entropy of the universe is continually increasing, a little bit all the time. The universe is expanding, and the entropy is growing. And so, some examples of entropy: you spill a glass of milk, you don't put the milk back in. Aging, you don't reverse the signs of aging. That is disorder of the body. Things start breaking down, they stop working, you get diseases, things like that. That is entropy. And then the last one is this building breaking down. At one point, it was probably a brand new, really nice building. And then as it sat there, it became a dilapidated building, started falling down. And those are all examples of entropy. Okay, so disorder, chaos. So this is going to end our our lecture over chapter 4. Make sure you've completed your notes and you're prepared to turn them in where you're supposed to, and you've completed all of the assignments for chapter 4.